Hello there, geometry folks. It's been a little while since I made a video, and it looks weird. I my the print is really small, and it's because I create these on one operating system and then come to another one now to create these videos. And so I hope you'll let me know if the printing is too small or stretched or weird. But yeah, I'm just gonna carry on until you let me know that it doesn't work. But hey, here we are. It's time to get ready for a quiz. And so here are the topics that we're going to be talking about on the quiz, or that you will be quizzed on. Everything from angles of polygons down to trapezoid theorems with lots of parallelogram stuff in between. These are the topics that should be in the table of contents of your notebook for this unit. These are the topics that it should have notes, questions, summaries, all that kind of stuff, so that you can dive into that material and be sure that you understand it well enough to do well on the quiz. If you have not taken some notes on one of these topics, or done some questions, or written some summaries, then why don't you take a little bit of time to get that done now, because that is probably the most useful way to get ready for a quiz. But if you have done all of that, then let's move on. So I'm going to take each of these topics one by one. I'm going to be revealing the theorem that's associated and then doing a problem that involves that theorem. So the first topic was angles of polygons. And the theorem basically goes a little something like this. The sum of the interior angles of any polygon is, it's a little formula, 180 n minus 2. And what we have to keep in mind is that n is the number of sides. And so you take the number of sides and you plop it in for n, and then you calculate accordingly. So an example of a problem like this would be this one that you see. Example, find the sum of the measures of the interior angles of the figure. So since we want to find the sum of the measures of the interior angles, we know we're going to use the little formula that does that. And so we know we're going to use 180 n minus 2, but then we have to keep in mind that we need to know the number of sides. And so we see this little figure here. So let's just count the number of sides. There's 1, 2, 3, 4, 5, 6, 7, 8. And so we're going to put an 8 in for n, and we have 188 minus 2. And then 8 minus 2 is 6, and so we have 180 times 6. And then the final step is to multiply 180 times 6, and we get 1080. And we know the sum of the interior angles of this octagon is 1080 degrees, and that is how you use the polygon interior angles theorem. From there, we went on to talking about parallelograms, and the first two theorems talk about opposite sides and opposite angles, and the basic idea is if a quadrilateral is a parallelogram, then its opposite sides are congruent, and then also its opposite angles are congruent. That's what these theorems tell us. And here's how you can use it. If you know that this is a parallelogram, which you do because that's what those little red markings mean, then you can use both of these theorems in this problem. The first theorem says that the opposite sides are congruent. And so if they are, then y plus 3 must equal 18. So y plus 3 has to equal 18, and it's just a matter of subtracting 3 from both sides to give us that y equals 15, and we're halfway done with the problem. Now the second theorem tells us that the opposite angles are congruent, and so 2x and 50 must be the same. So 2x must equal 50, and we can divide both sides by 2 to find out that x equals 25, and this problem's done. Now notice that I tackled the y value first. Doesn't matter. Those aren't interrelated. Even though those values are in the same problem, you're never going to say something like, 2x equals y plus 3. This doesn't happen. You got too many variables here, and you cannot possibly solve an equation like that. So bring together the things that the theorem tells you to bring together. All right, and then the part 2 of parallelogram theorems talked about consecutive angles, and it says that in a parallelogram, consecutive angles are supplementary, and also that the diagonals bisect each other, and those two theorems can help you solve problems like this. Well, the first one could. Notice we have a parallelogram here. That's what the red markings mean, and we're trying to find the measure of angle ABC. So that's this one here, ABC. So we know that if we take the measure of angle A, we're just going to conveniently call, instead of using 3 letters, just use 1. It's pretty much the same thing. If we take the measure of angle A and we add it to the measure of angle B, because consecutive angles are supplementary and A and B are consecutive angles, then we know that they have to add to 180. Now we know that the measure of angle A is 127 degrees, and to that we're going to add the measure of angle B. Now keep in mind that measure of angle ABC, we're just saying measure of angle B, so we don't have to write a bunch of letters all the time, but it's essentially the same thing. That's going to equal 180. So then we just subtract 127 from both sides, and we have that the measure of angle B, or actually the measure of ABC, which is what we're trying to find, is 180 minus 127. 180 minus 127 is 53. And there you go. There's the answer. And we should put ABC. There we go. Okay, and then you can also solve problems like this. We know that in a parallelogram, the diagonals bisect each other. This is a parallelogram, and so that means that this diagonal is cut in half by this diagonal, and so these markings end up being true. So now if I want to find the length of AE, which is this distance from here to here, I just need to notice that the congruent piece over here is 12 centimeters, and so AE must also be 12 centimeters. And then you also have DB, which is, let's see, where is that? Oh, it's this whole thing from here to here. Wow, okay. Well, if we know one part of it is 16, and this other part is exactly the same, this is also 16. And if we add those up, 16 plus 16 is 32, and so it must be 32 centimeters. Okay, that's how you use those two theorems. All right, the next topic was parallelogram theorems 3, and here's where we started taking the theorems, the 4 theorems that we talked about before, turning them around and using them to tell us whether or not the quadrilateral we're looking at is a parallelogram. And here's a couple of theorems about that. The first one says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. And then the second one says if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So this is a way to tell if what you have in front of you is a parallelogram. This helps us solve problems like this. For what values of x and y is quadrilateral PQRS a parallelogram? Well, we know from the theorem we just talked about that if the opposite sides are congruent, then it must be a parallelogram. So for example, if this side here was congruent to that side there, and this side here was congruent to this side there, then we'd know we have a parallelogram. And that's what we're being asked. What values of x and y make that possible? So what we can do is find those values by saying, well, what we want is for x plus 9 to be equal to 2x minus 1. What we also want is for y to be equal to 15. Oh, and that one's already done. That was easy. So we need y to be 15 to get a good start, but then we have to figure out the value of x that this equation will give us. So let's see, I'm going to subtract 2x from both sides, because that's how I like to start these kinds of problems. That creates a cancellation on the right side, bringing my variables to the left, which is why I like to do it this way. An x minus 2x's is a negative x plus 9 equals negative 1. Adding 9 to, oh, sorry, subtracting 9 from both sides gives me that negative x equals negative 10. Well, if negative x equals negative 10, then x equals 10. And now we know the value of x that makes this condition true. And so these are the values of x and y that will make the quadrilateral a parallelogram. Parallelogram theorems part 4 talked about more ways, a couple of more ways that you can find whether or not a figure is a parallelogram. If one pair of opposite sides of a quadrilateral are congruent and parallel, then the quadrilateral is a parallelogram. Furthermore, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. In other words, more ways to tell if the quadrilateral that you're looking at is a parallelogram. So we can solve problems like this with these couple of theorems. For what value of x is a quadrilateral CDEF a parallelogram? Well, it looks like we have some diagonals here. And it looks like one of these diagonals, CE, this one, is cut exactly in half by FD. Well, in order for us to have a parallelogram here, we're going to need to have each diagonal bisect each other. So what we need is for this part to be congruent to that part. So we're going to have to find the value of x that does that. And so let's find out what value of x will make it work. We have to have the condition where 5x minus 8 equals 3x, and now we're going to solve for x to find the value of x that will make this true. So let's see. This one's a little bit more complicated. I'm going to subtract 3x from both sides. It's not really more complicated. The steps are still the same. I'm using, I'm canceling, and then I'm doing the same thing to both sides, and that's good algebra. 5x minus 3x is 2x minus 8 equals 3x's minus 3x's is 0. I got rid of everything. And then I'm going to add 8 to both sides. I'm creating clever cancellations, doing the same thing to both sides. And that means everything's okay. I'm doing good algebra. And so then I have 0 plus 8 is 8. And dividing both sides by 2 gives me x equals 4. And that is the end of that problem because we found the value of x that makes these equal, which means that our diagonals bisect each other, which means that this object is a parallelogram. All right, then we kind of stopped talking about parallelograms for a little bit. Well, we're still talking about parallelograms, but we started specializing. We went from all parallelograms down to 3 specific special parallelograms: the rhombus, the rectangle, and the square. And the rhombus corollary, this is also where we started talking about corollaries, which are basically the same as theorems and postulates for our purposes. They're not actually the same, but for us, they work in much the same way. We can use them to find out things about our geometric objects. The rhombus corollary says a quadrilateral is a rhombus if and only if it has 4 congruent sides. The rectangle corollary says a quadrilateral is a rectangle if and only if it has 4 right angles. And then the square corollary ties it all together and says a quadrilateral is a square if and only if it is a rhombus and a rectangle. So you got your rhombuses, you got your rectangles, and then you have your squares, which are both rhombuses and rectangles at the same time. So knowing this can help us kind of categorize these types of special parallelograms. For any rectangle EFGH, is it always or sometimes true that FG is congruent to GH? Well, let's draw this thing and let's explore this. Here's EFGH, and we want to know if FG is going to be congruent to GH. That's what we want to know. And we want to know if it's always true or sometimes true in any rectangle. Well, it's not going to be always true, because if it were, then that rectangle would be a square, and we have rectangles that are not squares, and so we could have, something like this in a rectangle, which would mean that those 2 sides are not congruent, and so we're going to have to say that it's sometimes true. is sometimes true in the case of the square, but otherwise not so much. And then 3 more special parallelogram theorems. Gosh, I hope this stuff isn't so tiny that you can't see it. I'm really sorry. I turned on this computer and everything's shrunk from when I was working on it on a different computer, and it's a bummer. Anyway, the rhombus diagonals theorem says that a parallelogram is a rhombus if and only if its diagonals are perpendicular. And remember, perpendicular means that they meet at a 90-degree angle. So all diagonals of any rhombus will meet at a 90-degree angle. That's good stuff. And then a parallelogram is a rhombus if and only if each diagonal bisects a pair of opposite angles. So now, not only are the opposite angles congruent, but these diagonals cut them in half. And so we can have smaller and smaller pieces of knowledge to figure out all kinds of things about the angles of a rhombus. And then the rectangle diagonals theorem says a parallelogram is a rectangle if and only if its diagonals are congruent. And so we can use these theorems to solve problems like this. Find the measures of the numbered angles in the rhombus. Well, we're going to want to find the measure of angle 1, the measure of angle 2, the measure of angle 3, and the measure of angle 4. That's our goal, is to find these numbered angles. Well, this object, a rhombus, we know is a parallelogram. And so we know that opposite angles are going to be congruent. And so this angle D is going to be congruent to this angle F. Furthermore, since we know it's a rhombus, we know that diagonal cuts those angles exactly in half. And so not only do we know that the opposite angles are congruent, but we also know that all of these angles will be the same. So as soon as we find one, we're going to find all of them. Well, here's something else interesting. We know that angle G is 118 degrees, but since rhombuses are parallelograms, we know the measure of angle F and the measure of angle D because they're going to be the same. How we know that is that in every parallelogram, the consecutive angles are supplementary. In other words, if we take the measure of angle G and add it to, I don't know, the measure of angle D, for example, and that could be measure of angle F2, we're going to get 180 degrees every single time because consecutive angles are supplementary. So if we take the measure of angle G, 118, and we add to that the measure of angle D, we're going to get 180. So let's subtract 118 from both sides. And we get that the measure of angle D is 180 minus 118, which is 62. So now we know that all of angle D is 62 degrees. So in order to figure out angles 1 and 2, we just have to divide that in half. And what is 62 divided by 2? Well, it's 31, right? So we know that measures of angle 1 and 2 are both going to be 31 because the diagonal bisects angle D, and so each one has to be half of whatever angle D is, which is 62. But then we also know, because a rhombus is a parallelogram, that angle F is going to be exactly the same. It's going to be 62, and so 3 and 4 are also 31, and there you have it. Alrighty, and then yeah, another way of using these theorems is that this says this problem here, sorry, I got distracted. In rectangle QRST, QS, which is a diagonal, it's this one here, is 5x minus 31, and RT, which is this one here, is 2x plus 11. Find the lengths of the diagonals. Well, let's think about this. This is a rectangle. And in every rectangle, according to our theorem, the diagonals are congruent. And so we know that what we know about the measure of QS, for example, 5x minus 31, has to be equal to the measure of RT, which is 2x plus 11. And now we will do what we always do, solve for x. So we'll subtract 2x from both sides. That creates this cancellation. We have 5x minus 2x, which is 3x minus 31 equals 11. Adding 31 to both sides to create this cancellation gives us that 3x equals 42. And then we will divide by 3 on both sides, and x equals 42 divided by 3. Probably should know that off the top of my head, but I don't, and that's okay. I still got a math degree. So we know that x is 14, which is really great, because in order to figure out the lengths of the diagonals, we needed to know what x was. And then in order to find out what x is, we needed an equation. And in order to build that equation, we needed the theorem that told us that the diagonals of a rectangle are equal to each other, or congruent. And that's where we got our equation. So now we're going to take x and we're going to plug it in. And we really only need to plug it into one of them. So let's plug it into 2x plus 11. So we could say that RT is going to be 2 times 14 plus 11. 2 times 14 is 28 plus 11, and that's going to be 39, right? Well, let's just check to be sure we're right. QS has got to be the same thing. So QS is 5 times 14, 14 because that's the value of x, minus 31. Well, this one's a little bit more complicated, but we can still do it. 14 times 5 is 70. Minus 31, I think, is going to be 39. Yep. So we know that RT is 39, and QS is also 39, and that checks out because in a rectangle, the diagonals are congruent. All right, this was our last stop, these trapezoid theorems. These were the last theorems that we got, I think, just most recently. And they all deal with isosceles trapezoids, which are a particular type of trapezoid where the legs are congruent to one another. If a trapezoid is isosceles, then each pair of base angles is congruent. And trapezoids are funny, they have two bases. Both sides that are parallel to one another are called bases, and the base angles are the angles on either side of the base. If a trapezoid is isosceles, then each pair of base angles is congruent. And then we can turn that around, and it's also true if a trapezoid has a pair of congruent base angles, then it is isosceles. And then the last thing to talk about is its diagonals. A trapezoid is isosceles if and only if its diagonals are congruent, very much like a rectangle, same basic idea. And we can use that to solve a couple of problems. So it looks like we have a trapezoid here, and we're saying if EG, this diagonal here, if that is equal to FH, this diagonal here, is that trapezoid isosceles? And the answer is yes, because in a trapezoid, if the diagonals are congruent, then the trapezoid is isosceles, and that problem is done. The second part says, what values of x would make EFGH an isosceles trapezoid? Well, we know from another theorem that in order for a trapezoid to be isosceles, that the base angles have to be congruent. And so let's find the value of x that makes those two measures the same. In other words, let's take 5x plus 2 and set it equal to 2x plus 11 and see what shakes out for x, because that will be the value of x that makes those angles equal or congruent to one another, therefore making the trapezoid isosceles. So I'm going to subtract 2x from both sides. I feel like we've done this a million times during this video. 5x minus 2x is 3x plus 2 equals 11. And then you subtract 2 from both sides to get rid of that 2, and you have 3x equals 11 minus 2, which is 9. And then dividing both sides by 3, you get that x equals 3, and that is the value of x that makes this angle congruent to that angle. And then that is also the value of x that makes it an isosceles trapezoid. Because if the base angles are congruent, if just one set of base angles are congruent, then the trapezoid is isosceles. All right, y'all. That is all there is to it. That's a basic review of what we did, over the course of felt like forever because of all the changes to the schedule. But that's what we did, and that is the stuff that's going to be on a quizzes that's going to be dropped into Google Classroom tomorrow. Get some rest, eat and drink healthy, get your notes organized, do an assignment, but most of all, most importantly, believe that you can, because if you think you can, then you can. All right. I will talk to y'all later. Bye.